Welcome back. Hello, hello. Welcome back.
Exactly. Which one? Which team?
Hello? Can you hear me? Oh. Oh, but is it on? Welcome back. Welcome back to the final session. It's been such a great day with wonderful review talks giving us a full view, an overview of what is still to come in the next 3 days. And so today, in this final session, we'll have 6 talks, 3 going out to the higher redshift universe, and then we'll actually talk about what future observatories can do for this field in the final last talks, and we'll end the day with a discussion section. So without further ado, so we can start the timer, please welcome Emma Curtis-Lake, coming all the way from the UK, who will give us a review on the high redshift, low metallicity universe.
Hi, everyone. I just want to say thank you so much for the invitation to be here. To quote someone who is here, but I won't name them, said last year at a conference, the high redshift community has gone rogue. Where are all the low metallicity people? And it's true, maybe we've just sort of got a bit overwhelmed with all the data, but that means that I love being here and I love hearing all of your work. And it's amazing to be at a conference where you don't know all of the talks already. So I was asked to talk a little bit about the history of high redshift stuff, some of the uncertainties. I'm picking out some themes we've already heard of today. I'm adding to them. So we'll hear a timeline of progress the last 35 years, spectral diversity at the highest redshifts, NO enhancement with a little addition to what we've already heard today, stochasticity in star formation versus the escape of ionizing radiation, and of course, one of the things that JWST was built for, looking for pristine galaxies and population 3 stars. So here's a timeline of 35 years with over 3 decades, the 2 obviously most important events that I think everyone can agree on, launch of Hubble and launch of Webb. So going back to about 1992, this is when Seidel and Hamilton created the technique that was going to become an incredibly efficient mode for selecting high redshift galaxies, where you have a filter shortwards of 912 angstroms, and this is a model where they haven't applied the IgM absorption, but if they had, it would have no flux here. And filters redwards of that, we have no flux here, some flux here, and you can very efficiently find these galaxies. So at the time, they were looking for galaxies that could explain the absorption features in bright QSO spectra. And as I understand it, prior selections to look for high redshifts were looking for faint blue targets or using narrowband searches for Lyman alpha, which has also still proved to be very successful. And then 1996, first spectroscopic confirmations of sort of normal star-forming galaxies. This one's around redshift 3. So this is really validating that Lyman break technique. Moving on a little way, Great Observatories Origins Deep Survey starts around 2002. 4-band imaging around the optical from HST-ACS over regions already with existing X-ray and radio coverage. And these are fields that we are still pummeling away at in high redshift community. There's so much to find there in good south and good north, although we have broadened the net. And then September 2003 to 2004, data over the Hubble Ultra Deep Field. With incredible depths, around 29 magnitude over 270 hours, apparently surprising people, it kept finding galaxies out to further redshift the further you looked. And all of this is starting to give us really good samples of galaxies up to around redshift 6.5. So spectroscopic follow-up for these. Not too hard to get spectroscopic confirmations, often from Lyman alpha, so often sort of a single line. Some of them still have the continuum redwoods of this, but often relying on having that bright Lyman alpha line. And this was done by a few different groups, but Keck spectroscopy, adding hundreds more spectroscopic redshifts, and showing in an analysis that for increasing redshifts, the fraction of strong Lyman alpha emitters is increasing, and that suggested that that's from the intrinsic population. So maybe younger sources, harder ionizing radiation fields, we're getting stronger Lyman alpha. And if you extrapolate that further, you might expect to get more, but then maybe what happens when you enter into the epoch of reionization and encounter neutral hydrogen. And that's exactly where things started to get difficult. There were many studies doing this. I just picked this one because I like the fact that it also shows you that from the ground we're also getting the bright OH telluric features, making this really tricky. So not only does that make it tricky, but finding that the fraction of strong Lyman alpha emitters is decreasing because there's lots of neutral hydrogen around. So that's impacting this very bright line, which was really integral to spectroscopic confirmations. So we may be building up all of these lovely high redshift galaxy samples, but it gets harder and harder to follow them up spectroscopically. Meanwhile, lots of fun stuff has been happening up in space, where Service Mission 4, Wide Field Camera 3 installed. Soon after it, more time pummeled into the Hubble Ultra Deep Field. And now, with deep infrared imaging, it's pushing galaxy samples well beyond that redshift 7 limit. There are some large imaging surveys that happened, so wide area HST legacy survey with candles, a UDF-12 campaign, so that was hundreds more hours into the HUDF to look for the highest redshift sources, and then also Hubble frontier fields to make use of gravitational lensing and push to fainter magnitudes. But meanwhile, following things up spectroscopically, even if you're getting really lovely galaxy samples all the way out to redshift 10, 11, is really hard. And prior to JWST, this is the highest redshift spectroscopically confirmed galaxy, GNZ 11. We've heard about it a lot today. We already know what's in store for it. But it's confirmed just from this spectroscopic break. And actually, this is the modeling because it's a GRISM spectrum. You have to model all of everything else around it. And the reason this was even possible was because this was one of the most luminous high redshift galaxies on the sky. There were some other notable spectra, and Lyman alpha does peek through sometimes within the epoch of reionization, suggesting that maybe it's patchy. And occasionally there are some other UV lines there, so giving us a peek of what's to come. But there really wasn't that much. We were really waiting around for Webb. And even then, it takes a little bit of time, right, to get the near-cam data first before we can start following up on other interesting sources. And then in 2022, we were lucky enough in JADES to be able to put 2 objects on the mask that were further away than what Hubble could see and were selected from our near-cam imaging just weeks previously. So at 13.2, this became the new redshift record holder for the highest redshift spectroscopically confirmed galaxy. We, of course, broke our own record in, oh, I can't get there yet. We have to go back to GNZ 11. This came first. So only a few months later, we got move over, look at good north instead of good south, and get this stunning spectrum, which becomes the most shown spectrum at conferences that year, probably still conference at the minute. Okay. Then we break our own record. I do have that spectrum coming up, but the current record being this guy here, redshift 14.44. Some strong emission lines like GNZ 11. But then we're now into a different regime. So I think this should be the most shown spectrum for this year. It's stunning, right? So now we're getting to the point where it's not just these prism spectra. We can actually resolve these features. There's beautiful absorption features and starting to really get to grips with what's going on. This is at redshift 9.3. So from initial selections, ramping up in redshift to a point where we've got these beautiful things that actually people were getting comparable things at lower redshifts decades ago. So what does spectra reveal about high redshift galaxies? This is not a talk about the most luminous galaxies problem. I'm a bit agnostic to why they're so luminous. We find that the highest redshift galaxy is more luminous than what's easy to explain, but there's a bit of a microcosm there for things that are sort of happening in the general population. So if we just look at these galaxies, this one's quite bright. It's got some really strong emission lines, quite compact. GNZ 11, we all know that one now. Here's a new one. Relatively recent, 13.53 from, it's Pansy 14.1 from Donan's paper, Callum Donan. And then here's Jade's JWST 14, where we broke the limit. Again, not really strong emission lines. We have got an update on this one. I'll come back to it a bit later, where a strong emission line peeks through. And then this guy with strong emission lines. So the ones which are luminous but weak emission lines, generally a little bit more extended maybe, and the other ones more compact. We've already heard that from other talks as well, but it's sort of coming back to it again and again through various papers. So are these really different evolutionary pathways? Is it like some of them are going to do this thing and then continue on a different route to what these guys are going to do? Or is it just just the tail end of the distribution of what's happening in general? And there are different schools of thought. So for the compact nitrogen loud emitters, we have heard, but also Naidu compares the abundances of the compact nitrogen loud sources in carbon nitrogen to the aurora stars in the Milky Way. So these are in situ formed stars at redshifts around 4 to 6 in the Milky Way halo in very dense environments, and therefore saying maybe we're seeing globular cluster formation in high redshifts. For the extended weak emitters, Harikane draws parallels with slightly lower redshifts where very bright redshift 7 galaxies are extended and clumpy and maybe shown signs of mergers, and suggests perhaps some of these high redshift galaxies are being boosted in UV luminosity from merger activity. And then other studies are saying, well, what if there's sort of a broad continuum and you're just at one end of the regime with one and not with the other? And this is a really nice example going from in half-light radius, this are C4 strong emitters, which are also nitrogen strong emitters. And then these are stacks of C3 emitters, where it goes in increasing C3 equivalent widths, and therefore possibly, closer to a starburst. And so they're not necessarily two distinct populations, although they do see a slight bimodality just looking at size histograms. Now, we've heard about possible AGN contribution to these lines. There's a few different objects where this is being investigated. GNZ11 is an interesting one because it's for different reasons than the others. It's not just like, oh, it's got these high ionization lines, therefore must be AGN. The first suggestion of the AGN activity was actually from gas density estimates. So not seeing nitrogen for 1483 versus 1486, was suggested in Myelino 24 that this was very, very high density gas, more than 10 to the 9, and that you can reconcile this with modest line widths if you have a modest black hole mass. And then the morphology suggests a point source plus extended component. But this is not reproduced in all works, so these very high densities aren't reproduced necessarily in other analyses. And the MIRI spectroscopy doesn't reveal a broad component in H-alpha. But I leave this here because there is more to come. I don't think the end of the story for this galaxy. In terms of some of the other strong line emitters, so this one I didn't show in that little around before, but this is a slightly lower redshift galaxy which has X-ray emission, so an independent indication potentially of AGN emission, although in these sort of diagnostic diagrams it's sitting in a composite region. And Alba Vidal Garcia is here this week and is presenting a poster on Thursday on analysing this decomposing lines for star formation and narrow line region AGN activity. GHZ2 ionization lines, this paper suggested that you can reproduce the strong ionization lines if you have narrow line region gas for star forming. I don't think it has to be mutually exclusive that there be X-ray contribution, and it also consider that if they are in high density environments, that's probably the best place to be making and seeding the black holes that we see later on. Extreme nitrogen abundances we've heard a lot on, and this is a bit of an old slide that's, you know, if you want the most up to date now, go back to Daniel Scherer's talk earlier, it was excellent. But I'm bringing it up because I'm adding to it, the story. So just to recap, GNZ11 was the first to show a very extreme nitrogen over oxygen abundance at low oxygen abundance, and even with considering a 3-zone density model, some of these do survive. They're not completely explained away. And we've already heard from Danielle's wonderful talk about this galaxy and possible Wolf-Rayet features and Joule bursts as an explanation for the nitrogen abundances. So to add to this story, there's a paper by Alex Cameron using the JADE sample, and he's looking at nitrogen-2 emitting gas. So now it's not from the high ionization lines, it's from the low ionization line region, and none of them are reaching this very high enhancement region. So these are N emitters, but not in the sample. But some of them are reaching a moderate enhancement. So it's not easy to disentangle different scenarios, but maybe the extreme nitrogen-enhanced galaxies are at the tail end in a specific short-lived phase. Maybe it's stratified gas, or maybe there's still some Wolf-Rayet contribution. So a lot of these galaxies lie on the main sequence, so they're not so boosted in star formation rate. As Danielle said, that the nitrogen enhancement seems to correlate with star formation rate density. So, but maybe you just don't get such high sampling of the high mass end, and you can still get moderate enhancement. Moving on to something a little bit different and going back to the galaxies that didn't have any emission lines, or at least no significant emission lines. Once you get into that regime, it's a little bit hard to always know what's going on. So if you've got a prism spectrum, you probably resort to SED fitting, and the handles that you have to turn there are like ages, dust if you want. You can turn off star formation recently, and you can allow for escape of ionizing photons. And it's quite crude, and these things are really degenerate. You generally can't tell very well. This was just a case where it's the spectrum, when we came back to it, so this was JWST 13.0, was really quite blue. And then once you get into that regime, it's harder to explain it without taking away some of the nebular continuum, which would redden the UV slope. And so actually it made sense to invoke a high escape fraction. Not that we'd be claiming that we really think it's this high, but that it was a proper tension in the modeling where you had to allow for this. And to be fair, you do want some of those ionizing photons to escape to reionize the universe. But the other possibility, which has been gaining in traction, is stochasticity of star formation, and that when you have weaker lines or no lines at all, maybe you are in a lulling phase. So maybe your burst has just finished. And that's where this beautiful spectrum allows one to break that degeneracy somewhat. So it had a very low Hb to equivalent width, around 25. It's very luminous. It's expensive. But it's got absorption features from the ISM, which indicates a really high neutral gas covering fraction, which makes it much less likely that you've got a high escape fraction of photons from the galaxy. And it actually starts to make sense when you've got data this beautiful to actually have multiple bins in your SED modeling. And so they indicate that it could have had a burst very recently, but it's on a decline. And even to the point where it's starting to replicate some of the stellar photospheric features. And then finally, moving to the slightly more difficult regime of looking for very special galaxies. If I were to leave you long enough, maybe you've already seen what these ones have in common. Maybe you just remember what my talk's meant to be about and what we're meant to be ending on. But all of these three spectra, the thing they have in common is that we're not seeing any metal lines. And these are not three of the lowest metallicity candidates so far. This one is. And then this one's slightly different. I'll come back to it. Here's a summary for you all of some of the candidates for lowest metallicities at the minute. Pretty far away from pristine. Often when you've got an upper limit there, it's about an upper limit on your metal lines, which means that you have to just keep going deeper and deeper to beat down that limit, which is hard to do, right? Some of them, this one's interesting, a photometric selection. So James Trussler also does this, where looking for a photometric constraint on the continuum, they actually suggest that this object has incredibly high equivalent width in H alpha. But I'm going to come back to, I'm going to end on this one. So it's not the most metal poor, highest redshift. So this guy here, when we got the spectrum for GNZ11, you'd see on our Slack messaging, message from Roberto at a random time, showing the spectrum, pointing to a little smudge above GNZ11 going, helium-2, I'm putting in a DDT now. And that, I think we got 2/3 of the data or something. The line was there, but you can't confirm it to be helium-2 without anything else. You can't really confirm the redshift. It's a line. We expect some lines. But then there's this data from Hannah Ubler in a different survey with H gamma. So now we can say, okay, here's GNZ11, here's helium-2 emission, not so far away. And we've been told by various simulation theorists that if you want to look for pristine gas, maybe you want to look around in big halos or near AGN or something with big outflows that's creating the perfect environment nearby for star formation, but from pristine gas. So they were directly looking for it. Again, just looking at a spectrum and looking for your signal to noise over your oxygen lines, your metallicity lines, we're nowhere near the limit. But it's got a strong equivalent width of helium-2. And looking at these, this is where the evidence is really coming from that it might be evidence for pristine gas or POP3. Cannot discount direct collapse black hole. The thing is, I'd hope that people today, if they've listened enough and listened to Peter, should be a little bit worried. So if we want to go beyond just the signal to noise on O3 or other metal lines, and we want to rely on photoionization models and to plot things on there, we have to make sure that our photoionization models can reproduce helium-2. Otherwise, if we're saying that we're not reproducing the helium-2 and can only do it with POP3, we're in a little bit dangerous territory. And the one thing that was said earlier was that photoionization models are not reproducing strong helium-2 emitters at low redshift. So, but it is with equivalent widths of the Balmer line to the helium-2 lines. I think that's where a lot of the evidence is going to be pointing for a long while, rather than just the upper limits on your oxygen abundance. So with that, it's the end of the talk. It's really more sort of highlights and themes with looking at the spectral diversity at the highest redshifts. Maybe everything is just along a spectrum when we're seeing the most extreme galaxies at one end of it. And there's no reason that they can't be bound, globular clusters, etc., highest densities, density regulated star formation even. But they show N over O enhancement in some of the strong line emitters, not all of them. We have an uncertainty when we don't see those lines, sometimes between stochasticity and the escape of ionizing radiation, but that's where this deep spectroscopy can start breaking those uncertainties. And with the search for POP3, the search is ongoing. There are some really lovely candidates there with really good limits on over H, but maybe we need to go further than just the limit on oxygen to look for evidence for POP3.
It was a beautiful overview. Questions? Do we have any constraints at all on what the possible duty cycle for the bursts due to some kind of stochastic star formation history would be?
I would want to reread papers, and I wonder if Danielle could answer that at the minute, but she seems to be looking at a computer instead. But I think not directly yet. But the thing is, we're seeing intense bursts, but then you can't really constrain the ages that well without these kind of very high resolution spectra of the downturn. So you would want to do it from the fraction of the population, but I don't think we have good statistics on that yet.
Aida.
We can reproduce nebular helium-2 if the metallicity is 1 Zwicky 18 like, and we have very massive stars, and we trust the models. We can also reproduce it if there is a very high 90% escape fraction of ionizing photons. I don't know if Oscar is here, which we think is unrealistic.
Yep.
Yeah, so I'm curious about what other types of scenarios can explain the strong emission without metal lines. Isn't necessarily. Could this be like a Henny's Warwarp that has pristine gas or something like that, where there's an AGN and not actually star formation causing the ionization, or is it just that we don't understand the gas condition?
I think I missed some of that, what you said. You're asking about the...
So the POP3 candidate.
Ah, okay.
So I wasn't super clear on the reasons for the uncertainty. So is it because you might have just gas there and the illumination for the ionizing?
Yeah, the only thing that we know is that there's a hard ionizing source because there's helium-2 and it's a high equivalent width helium-2, so there's lots of ionizing photons. Those are sort of like our
That's the ground truth. Thanks.
Okay, let's thank Emma again. So let's welcome Yuki Isobe. He'll tell us about tracing early metal enrichments in the era of all this amazing JWST data. Please take it away.
Okay, thank you for introduction. Hi, I'm Yuki Isobe, JSPS fellow in the University of Cambridge and Waseda University. Yeah, today I'm excited to share such a treasure trove of metals discovered by JWST at high redshift. Okay, probably I don't need to say that it's really interesting to see the Innova enhancement at the subsolar metallicity of the, observed in the high redshift galaxies, which cannot be explained by the standard scenario of chemical evolution combined with the quark-collapse supernovae and HB stars. But the question here is the abundance ratios of typical high redshift star-forming galaxies. Indeed, I cycled the some of the Innova enhanced galaxies with the agent signatures reported, such as broad lines. So we decided to explore the connection between the Innova enhancement and AGN. We used a large data set of the J's whose final data release is already out recently. And briefly, JWST has over 3,000 robot spec-Z sources at redshift 0.14 in the good south and north field. And JWST observed the wide waves range of 0.6 to 5 micron with both R100 and R1000 data. Here I show the distribution of the star formation rate and stellar mass of the around 600 JWST non-AGN sample at redshift 47, which is distributed close to the main sequence of the same redshift shown by this lines, which is in contrast to the magenta data point shown in the redshift 4 individual sources with temperature-based chemical abundances. So by leveraging this data set, we can explore the less biased and more general population of star-forming galaxies. But of course, here I show the typical spectrum of the high redshift star-forming galaxies, which doesn't show the oxygen 3 oral line and the carbon 3 detections. All right, then one simple but powerful way to overcome this is to stack. Like this, we can improve by stacking around 600 non-AGN sources at redshift 47, we significantly improve the SN ratios, which enables to detect O3, 4, 3, 6, 3, carbon 3, and even silicon 3 here. Now, in this spectrum, we don't see the nitrogen 3, 1750 here, but what about the R100 data, which has a longer exposure in JWST surveys? All right, then here's the result. We stack the sample, we separate the sample into type 1 AGN and type 2 AGN, non-AGN, and then stacks. And here we show that the nitrogen 3 is detected only in the type 1 AGN stack, but not in the non-AGN stack. So we derived the Innova ratios by using the UV emission line nitrogen 3 and oxygen 3, as well as using the R1000 data to obtain the temperature and density. Okay, then here's the result. The red circle shows the Innova ratio of the type 1 AGN stack, which shows the supersolar Innova ratios comparable to those of the Innova enhanced galaxies. We also plot the Innova ratio as a function of sulfur-based electron density, and our AGN stack has high electron densities compared to the non-AGN stack shown here. It's also resemble to the Innova enhanced galaxies. We interpret that this is the dense environment is a key for both Innova enhancements like Wolf-Rayet stars or kind of massive stars enrichment and black hole seeding and growth. On the other hand, we also show that the stack of non-AGN sample here is only an upper limit at the solar abundance, and the densities are also less dense. So supersolar Innova ratio may not be common in high redshift star-forming galaxies. All right, then what about other chemical abundance anomalies? For example, there are some reports of the supersolar carbon to oxygen ratio in some metal galaxies. Our stack of the non-AGN sample comes here, which is rather 0.7 dex below the solar composition, and even below the individual measurements of redshift 0 galaxies, gray dots, and redshift 4 individual galaxies, magenta 1. And we compare the Cherokee Milky Way chemical evolution model with this solid curve. Of course, this chemical evolution model is not adjusted for the high-Z galaxy observations, but still, we see the exact alignment with the chemical evolution model. At this low metallicity flat line, which is dominated by quark-collapse supernovae E's. So this suggests that the general population of high-star mean galaxies has gas composition with negligible delayed enrichment by AGB stars. Actually, this stack also shows a low argon to oxygen ratio, suggesting a negligible type 1 supernovae, which will be talked in Noah's talk and also Tom's talk later. And also, yeah, I'd like to share another interesting result about the silicon to oxygen ratio, which is sensitive to dust depletion. Our stack shown here, and it's actually significantly below than the chemical evolution model without the concentration of dust depletion here. But the comparable to those of the dust depletion taken into account. And yeah, it's also interesting that our measurement is also below the high-Z individual galaxies, JNZ11 RxCJ is the negligible dust reddening. So combined with the low carbon to oxygen ratios, we interpret this result as a kind of rapid dust formation by quark supernovae in the general population of star-forming galaxies in 10% solar metallicity. Okay, what about then ion to oxygen ratio? It is extremely hard to measure, and we don't see any detection of the ion 3 in the all sources, but we separate samples into several property bins, such as specific star formation rate, to explore the detection. And actually, we detect the ion 3 emission in the high specific star formation rate stack, which shows a high ion to oxygen ratio here, which is hard to explain by the standard chemical evolution model. In fact, actually, this kind of high ion to oxygen ratio is also reported in a redshift 0 extremely middle pole galaxies that I worked in before JWST. It motivated us to explore the actual high redshift EMPG sample. Actually, as in Emma's talk, we see the kind of several high redshift star-forming galaxies exhibited low, extremely low R3 values, such as LAP1 and QSON1, as shown by these colorful data points. And some of them even have the non-metal lines, such as Amore 6, LAP2, and Hebe. And some of them has a kind of hint of POP3 stars, like high carbon to oxygen ratio and strong helium 2. But the question, the problem here is that the measurement of the metallicity, I mean the high-Z strong line method, are not well calibrated at the low metallicity regime below 7.3, because there's only few galaxies with a direct temperature method in this regime. And also, there's a problem that how to extrapolate the calibration. I mean, someone using the potential models, someone using the high-Z calibration, and someone using redshift 0 calibration. Each of them has provide different metallicities for the methodological systematics in the low metallicity end. So we decided to extend the metallicity calibrations. We stack alternate data to detect O363 of low metallicity galaxies. In addition to J's DR4, we use the new data of the data dark holes at regime 1 to 10, which target around 800 faint sources with 9 to 10 hour exposure to so deep. And we stack these sources in means of strong line metallicities using the Mirko's the strong line metallicity technique. And here is the stack of the lowest metallicity bin, the 12 plus local weight below 7, 2% solar. And here we see the detection of oxygen 3, 4363, which provides the temperature-based metallicity of 7.0, which is entering the regime that the high-Z strong line calibration are not very calibrated. So we recalibrate the strong line method by using our stack spectra. And these red circle shows the stack measurement in beams of metallicity, and the orange one shows the beams of stellar mass. And we fit them in the best fit the polynomial function shown by this red curve. And compared with the current high redshift calibrations shown by this yellow, our stacks and calibration systematically have lower R3 values. indeed, we also compare the O32 index, and it also shows the lower O32 values than the high-Z calibrations, which means that, which suggests that requiring the faint or line detections can bias sample into the higher ionization. From a different point of view, in the low-metallicity branch, our new calibrations provide a slightly higher metallicities, which means that we can provide a more conservative selection of the EMPG candidates. Using our calibrations, we obtain a mass metallicity relation of the J sample shown by this contour. It is below the redshift 0 mass metallicity relation and exactly aligned with the mass metallicity relation of zoom-in simulations. And we select 50 EMPG candidates with a triplascopics down to 6.7, around 1% solar at redshift 1 to 9 from the around 2,500 sources at the J's, dark holes, and Oasis deep 28-hour observations. And our EMPG candidates distributed here systematically had a lower metallicity than the high redshift mass metallicity relation. To discuss the origin, we compare the zoom-in simulation more closely, and this curve shows the evolution track of the single simulated galaxies with a vertical drop at several points, suggesting that the pristine inflow. So our EMPG candidates may be on the onset of pristine inflow, is like this. And also, yeah, we take the EMPGs from the literature, many of which are length, and we adapt our calibration for consistency. We confirm that there's a large scatter in the low mass end of the mass metallicity relation, which is also predicted in the simulations with the stochastic star formation history. So this kind of large scatter can be given by produced by the stochastic star formation in the preferentially in the low mass region. Okay, here's a summary, and I'm happy to take any questions.
Questions? Yes.
Really, really great stuff. These sources that are, or the stacks that are rich in iron to oxygen kind of goes, I guess, what we expect.
Sorry, iron to?
The iron to oxygen.
Okay.
The enhanced iron to oxygen. Do you have a physical motivation for what could be driving that higher ion?
That's a good point. Actually, we don't know the exact answer of the enhancement ion to oxygen ratio. Actually, there are mainly two ways to explain the high ion to oxygen ratio, one of which is type 1 supernovae with the early delay time, and the other one is to assume the energetic supernovae like pair instability supernovae or the hypernovae. But actually, we plot the ion to oxygen ratio as a function of different abundance ratios, such as the silicon to oxygen ratio and argon to oxygen ratio, and our measurements actually offset from any of the chemical abundance, chemical enrichment models. So we are now discussing the answer yet, but anyway, we see kind of very, how to say, exciting and unknown star formation in the high redshift.
I think we have time for one more question if there's one. Yep. JT.
So considering your talk, very nice talk, and the last one, and that there are basically many of these candidates, most of them are selected from the same set of fields.
Okay.
I wonder if it's possible to put a number on the ratio of cosmic number density for these extremely metal poor galaxies versus the top 3 candidates. Even if it's a very rough order of magnitude number, can you estimate cosmic number densities for these very different fields?
Yeah, that was a good point, and it's really nice to see. Yeah, at this moment, we have a kind of 150 is around 2% of the sample be classified is a EMPG candidate in our threshold. But yeah, of course, we know the exact number of the exposure time, so we can correct for the kind of the observational depth of that, then calculate the number density of the such kind of menopause galaxies. I'm not really sure whether this kind of sources originated from the kind of POP3 nature, because the stellar mass is a little bit higher than those predicted by the POP3 models.
Okay, let's give Yuki another hand. Okay, so for our final high talk today, we have Thomas Stanton. He'll talk about chemical enrichment in the early universe again with JWST.
One more time. So yeah, I'm Thomas Stanton. I'm a former PhD student, now postdoc at the University of Edinburgh. And I'm going to be talking about some of the work that I was doing throughout my PhD, looking into how we can investigate the chemical enrichment of the early universe, specifically with the Excel survey. So the Excel survey was a Cycle 2 program led by Adam Carnell and Fergus Cullen, targeting star-forming and quiescent galaxies in the UDS field, which we attained deep medium-resolution grating spectra for about 350-odd galaxies. I'm going to mainly talk about the star-forming sample, for which I'm showing an example on the right. This is a galaxy at redshift 5, for which we get nice, clear detections of all our favorite strong emission lines, but also detections of the crucial 4363 line and other auroral lines that we need to measure abundances more directly in the high-redshift universe. So I'm surprised that I'm the first person to show this figure at a conference. Usually it comes out straight away. But we have a whole different array of elements that we can talk about. But simply to start off with, I'm going to talk about what we traditionally think of metallicity, which is oxygen. And in particular, I'm going to focus on a paper that we published earlier this year, looking into two key oxygen scaling relationships, the mass metallicity relationship, as well as the fundamental metallicity relationship. We've had some nice primers on the mass metallicity relationship already, but just as a bit more information on the fundamental metallicity relationship, this comes from the sort of idea and predictions from gas equilibrium models that galaxies will fall on a fixed plane in stellar mass, star formation rate, and metallicity space. And any deviation from this plane, such as is being observed with high redshift, potentially indicates some breakdown in the equilibrium processes regulating galaxy evolution. So to talk about that with Excels, I'm first going to go into the mass metallicity relationship. We were able to measure the gas phase metallicities of 65 star-forming galaxies at redshifts of 2 to 8 using a calibration scheme that we explicitly tested against the Excels galaxies to know that it produced good metallicities. Splitting our sample into two redshift bins, we've got 2 to 4 on the left and 4 to 8 on the right. We found clear evidence of a mass metallicity relationship in both bins, which showed sort of consistent slopes, but a mild evolution in normalization as you go to higher redshift. And this is consistent with what was being seen at the local universe out towards redshift 3, pre-JWST. But we now have an absolute wealth of studies that are looking into this, and we can begin to really study the evolution of this relationship in a bit more context. I want to highlight that this is very much a qualitative comparison. Each sort of individual literature study and simulation will have different treatments of selection functions, how they estimate metallicities and things like that. But if we look at the left panel, which is the low mass slope of the mass metallicity relationship as a function of redshift, we can kind of see that the slope appears to generally sort of fall between a range of values, doesn't show any evidence of a strong evolution with redshift. What this is telling us is that the slope is approximately sort of set by about a redshift of 8, and the processes that regulate the slope aren't necessarily changing significantly over this epoch. So this is seen both in the observations, which the data points are in blue, but also seen across the different simulations as well. Instead, if we look at the normalization, we see, as we would expect, a clear evolution towards a lower normalization at a fixed mass with increasing redshift. And whilst this appears in this sort of panel to be very well matched by the simulations, I'm being a bit devious. These have all been rescaled to run through one of our points. If you look at the absolute metallicity evolution within the simulations, you get a very, very wide range of values. And especially towards the higher redshifts, you begin to see some really clear deviations, indicating that it's not just observations, but simulations we've got to do some work with to sort of reconcile our understanding of chemical evolution in the early universe. Turning now to the FMR, I'm showing a series of panels here. Each of these shows the difference between the measured metallicity and the metallicity predicted by a local FMR, in this case, Andrews and Martini 2013. The left panel shows our strongline calibrated data. In the center panel, we're just showing the direct method data, just as another test of sort of metallicity method. And we're also showing, in addition, all of these individual smaller gray points. These are other galaxies from the literature, and where possible, we've binned or stacked these into these black and white points. Excels finds consistent results with previous studies looking at this. Basically, around a redshift of 3, we begin to see a deviation towards lower gas phase metallicity than the FMR would predict, potentially indicating this breakdown of the FMR. It's also worth noting, though, that if we look in the right panel, which is comparing with simulations, we see agreement with some of the simulations that predict a weakly evolving FMR. And what this means is that you'll have an FMR in your simulation at a given redshift, but it's not necessarily going to match what you have at redshift 0. So for example, we saw a particularly nice agreement with illustrious TNG. However, this offset is also potentially very, very physical, driving why these galaxies are not aligning with the FMR, and a variety of physical explanations have been proposed for this, such as higher gas fractions, pristine inflow, sort of overwhelming star formation and causing net dilution of the metal content within the ISM, or bursty star formation driving more metal-enriched outflows. We raised another potential case to further complicate matters. So in these panels, I'm showing essentially your star-forming main sequence. You can pick either panel to focus on. They're just 2 different FMRs. And in the histograms, I'm showing the samples that have been used to build those local FMRs. And these are shaded by the logarithm of num density of the galaxies that go into those. Our data is plotted over the top in blue. We have the stacks from the previous panels, as well as local blueberry and green P galaxies in green. And these are just redshift 0 galaxies that have properties that more mirror high redshift galaxies and are similarly offset from the local FMR. And what we can see, and this is perhaps most clear in the right panel, although because of the logarithmic scaling, I want to stress that in the left panel, these bins are very, very sparsely populated, is that we're comparing 2 populations of galaxies with vastly different properties. And it's entirely possible that this offset, at least in part, is driven by this very significant extrapolation between galaxy properties. Hopefully, with the next generation of instrumentation, particularly large ground-based surveys with instruments such as MOONS that will pull in thousands of galaxy spectra at cosmic noon and hopefully span these properties more, we'll be able to really assess whether or not this is an effect or if we're looking more towards physical effects as well. So moving a bit beyond oxygen, we've had some great talks on some other elements, such as these ones, and I don't think I need to say that all of these different elements have different production mechanisms, and these occur on different timescales. And by comparing these different productions elements, we can sort of use these as chemical clocks to get a handle on our enrichment history, as well as our sort of star formation histories. So we have elements like oxygen and neon. These are alpha elements primarily produced through core collapse supernovae, and this happens relatively rapidly after the onset of star formation. I won't talk about nitrogen and carbon, but these sort of fill in your sort of intermediate timescales due to enrichment by AGB stars. And you have elements such as iron, which are produced primarily through type 1a supernovae, and these are delayed by about at least sort of a giga-year or so on average from the onset of star formation. I've linked argon and sulfur in here as well because these have non-negligible productions through type 1a supernova despite being traditional core collapsed elements, 34% for argon and 25% for sulfur. And yeah, we can begin to look at these elements and sort of see what happens. So to sort of demonstrate how we could use these elements as chemical clocks, I want to draw your attention to the schematic on the right. This is just the predictions of chemical evolution models tracing 3 different local systems in the oxygen to iron versus iron plane. And whilst this might be against iron, you can also kind of think of this as a temporal axis, as at low iron abundances in early times, you won't really have type 1a enrichment bringing up your iron abundance, and your sort of abundance patterns will reflect an enhanced oxygen to iron sort of consistent with the plateau. Once you hit this sort of circle point, which is the low alpha Ni, your type 1a enrichment begins to drive up your iron abundance and bring down your oxygen to iron, forming this characteristic Ni shape. And what we found in a paper I put out in 2024, where we measured the oxygen and iron abundances simultaneously for individual and composite galaxies at redshift 3.5, is that our galaxies very neatly follow these trends, implying that they are sort of consistent with the sort of abundance patterns being dominated by core collapse supernova yields and massive stars. And this phenomenon, I should also say, is often referred to as alpha enhancement. We're looking at it with just oxygen and iron here, but in the local universe, they use alpha. Maybe more correctly, should be referred to as an iron deficit, as we're not looking at an enhancement in oxygen, but a deficiency in iron. And this has some implications I'll talk about in a couple of slides. But iron abundances are tricky at high redshift. You just showed us you can stack 500 and something galaxies, and you may only get a couple of detections. So this prompts the use of alternative traces of type 1a. We talked a little bit about argon. I ran one of the sort of pilot studies for these early on into Excels, where we took 8 star-forming galaxies at redshifts of 1 to 5, finding that they were typically deficient in oxygen to argon. This is sort of mirroring our oxygen to iron plane, where we have oxygen to argon versus argon here. And we use neon in this particular sample as a control element, as we would expect neon and oxygen to enrich along the same pathways. And indeed, we found that the neon to oxygen ratios we got were consistent with other local galaxies, high redshift galaxies, the solar value. So we're getting a very good handle on how these different elements are enriching. In my last couple of minutes, I'm going to talk about my current work, which has been trying to figure out what this means if you're just looking at a galaxy's nebula emission and things like that. To demonstrate how this links to abundances, I'm using the BPT diagrams. I'm showing a nitrogen-2 one on the left and a sulfur-2 one on the right, where local galaxies form these very, very tight sequences in this plane. So I'm showing, for example, here DESI, DR2 in these contours. And commonly, these diagrams are used to separate star-forming galaxies in AGN. You know, you either use the star-forming sequence to sort of form a separation line, or you use some sort of photoionization modeling to basically figure out what regions of this diagram are occupied by star-forming galaxies or AGN. High-redshift galaxies complicate this because at these galaxies are typically offset towards higher ionization and higher R3 values than your local samples, in many cases crossing the lines and making your separation of these samples complicated. The reason this links to chemicals is that this offset can be understood through alpha enhancement, as an ion deficiency in your stellar population will drive a harder ionizing spectrum than if your stellar population wasn't alpha enhanced. Yet to date, no photoionization modeling fully encompasses the effects of non-solar abundance patterns and alpha enhancement. So I've spent a lot of time running Cloudy. We've taken some stellar population models, and alpha-enhanced models are becoming available. We're currently using the non-ones, as they're not always fully enhanced in the ionizing part of the spectrum. We've been extracting their ion abundances, and we've been using the chemical evolution models of Chiaki Kobayashi, which we see very, very nice agreement with at high redshift, to create these alpha-enhanced abundance patterns. And I'm showing here the difference between a typical alpha-enhanced abundance pattern and the solar pattern at a fixed ion abundance, where in the shaded columns we see these enhancements of our sort of key elements here. Running these through Cloudy, we then investigated, can we reproduce the shift in the BPT that we get purely by changing the underlying chemical composition of the gas? And we can. So on the left, this is a sort of no alpha enhancement case, sort of what you would see with your classic photoionization models. As you move towards the right, we increase the alpha enhancement, which we're parameterizing by this OFE ratio, and we naturally reproduce this offset towards higher R3 values. This therefore has calamitous implications for how we could use the BPT diagrams to separate our star-forming galaxies, and that's on top of AGN also mixing into star-forming sequences and stuff. So here I'm showing the Excels galaxies on the BPT, where each of these panels is just a different degree of alpha enhancement we get from fitting our models. A no alpha enhancement case, you sort of would find that a bunch of your high redshift galaxies, these are the redder and bigger points versus the smaller and bluer points, you would typically label as having some sort of AGN contribution. But they are also formally consistent with star formation if that stellar population is alpha enhanced. And this really just means that these diagrams are very complicated to use to separate this out, and we really need some new diagrams, and there's been some great work happening on this already. I think that is my time, and I will leave you with my summary.
Cloudy.
I've been saying that too, so.
Questions for Thomas?
Does the alpha enhancement increase also the equivalent width of the lines or border these BPTs?
I would expect that yes, that is something we haven't gotten around to testing yet, but one of the applications we're going to look at in the modeling is trying to incorporate these into SED fitting codes like bagpipes, seeing how that affects the equivalent widths you get out, and if you can sort of reconcile some of the extreme properties you get by allowing for alpha enhancement.
Really nice talk, and I really love this alpha enhancement piece. It's really great. But I had a question about on the FMR piece. I mean, you talked about this offset and how we're in a different part of the parameter space. Do you see an FMR in your data at high redshift? Like, does star formation reduce the scatter in the same way as it does, or is it just consistency with like the direction? Yeah, that's what. Okay.
Yeah, we ran a series of parametric and non-parametric tests using the strong line and also direct method metallicities. Well, we sort of see if we just simply split the sample at its median SFR, you see some evidence that there is some separation there. Statistically, this isn't formal. It's not formally statistically significant. We happen to find an alpha value of about 0.33, which isn't far off the original Minucci value. But the reduction in scatter we saw was, at the sub 10% level compared to the 70% you're seeing in the local universe. And also with sort of non-parametric tests, looking at the offset from the star-forming main sequence stems that are tentative evidence, but we didn't have the number of statistics to really get to it.
Okay, let's thank Thomas again. Okay, so now we're going to transition into 3 talks that will help us think about what future observatories can do for this field. And I just want to remind everybody that you have a Google Doc linked to the Slack channel where you can put your ideas. We'll also have some audience interactive activity at the end since we're getting close to the end of the day. So keep that in mind while we welcome our first speaker who will tell us about the Roman Space Telescope. Christy McQuinn. Please give Christy a hand.
Okay. Okay, great. Thanks, Janice. All right. Mike, okay? Yeah, okay. All right, so I'm going to talk to you about the Nancy Grace Roman Space Telescope, which is coming soon to an L2 near you. In fact, it's almost ready to launch. It is under budget and ahead of schedule. In fact, NASA keeps moving the schedule earlier and earlier. And right now we have a launch readiness date as early as the end of August. There's a picture of Roman in the clean room, taken not too long ago. And it's just worth pointing out that the telescope meets or exceeds all science requirements. So Roman is really an unprecedented NASA survey observatory. It has a mirror the size of Hubble, which means that you can expect the image quality and sensitivity that we get from Hubble, but it is a field of view that's 200 times larger than the WFC3 IR camera. What I'm showing you here is a picture of the Hubble image of the pillars of creation, and we're zooming out to an individual footprint, one individual pointing from the Roman Space Telescope. But in addition to being just a larger field of view, the telescope is built in a way that it can tile the sky quite quickly. In fact, it can tile the sky 1,000 times faster than Hubble, which means that with every 10 months with Roman, we'll be getting roughly the equivalent of 1,000 years of observations with Hubble, from Hubble. There's some other differences. Roman looks in the near-infrared. We have 8 broadband filters in the near-infrared and 2, we've slitless spectroscopy with both a grism and a prism. So Roman is designed for delivering science for everyone, but it's worth noting that there are 4 extensive community-defined surveys that are already ready to go for the observations. And it will map the universe in high resolution. And this is just a quick overview of what these 4 community-defined surveys look like. In blue, we have the wide area survey that will be great for studying dark energy and creating a map of dark matter. In red and orange, we have a time domain survey, which is going to be particularly relevant for studying supernovae at high redshift and the expansion of the universe. In the center here in orange, we have a study of the galactic bulge in time domain approach that'll study exoplanets. And finally, in yellow, we have the galactic plane survey defined, which is a shorter survey, but it's going to be amazing. So in more detail, the wide area survey is what we call our big map. And from this, it'll be 1,000 times larger with deep imaging and spectra than Hubble's largest deep survey. Shown here in sort of the mosaic of the 18 detectors of Roman are just cartoon pictures of the different science that is made possible from our big map, including things like 600 million measurements of galaxy shapes and 11 million spectroscopic galaxy redshifts. But this is probably the one that's going to be of most interest to this audience that's going to be hunting for metal poor galaxies. The time domain survey we call our cosmic movie, and it will create a deep stack of co-added images that will cover an area about 100 times larger than Hubble's deepest, largest comparable survey. We're expecting to discover about 20,000 type 1a supernovae, and this is out to higher redshifts, to maybe redshifts of 3 or 4 or 5, giving us a direct measurement of the Hubble constant through this method for the first time. We're also expecting about 100,000 transient detections. In the galactic bulge time domain survey, we think of this as our treasure hunt. We're expecting to get about 1,000 bound and free-floating cold exoplanets. And so this will be sampling and studying the demographics of exoplanets that have been really difficult to find with other methods, including Earth masses in colder, more habitable zones than what we found previously. And we're also expecting to detect through the transit method about 100,000 exoplanets. And for comparison, the current census is around 6,000. And finally, the galactic plane survey. We're going to be covering about 35% of the galactic plane. This will be the highest resolution map of the Milky Way to date. And in this area, we're expecting to detect about 20 billion sources, which is larger than the cumulative sum of all sources detected and cataloged in the history of astronomy. So how do you harness the power of Roman? How do you go from these big data sets to scientific discovery? We have just a cartoon graphic of what the per data rates look like. So for Hubble, we get a couple of gigabytes a day. For Webb, we're getting about an order of magnitude larger. For Roman, we're expecting almost 1,400 gigabytes of data per day. And so here at the Institute, we're thinking about how to make it easier for the scientific community to wrangle that size data and do their data analysis. And it's not just us at Space Telescope. We have a sibling science center out at IPAC that's also doing some of the work to prepare the data for you, the science community. And I want to highlight a little bit about the data products we're making and who's doing what. This is a different mode of operating than what we're normally doing for flagship missions, so I think it's worth just kind of explaining a little bit. Here at STScI in the Science Operations Center, this is the area of work that I lead. We are responsible for taking the data from the telescope, creating uncalibrated files from it, and then calibrating all of the data for you. We call those files level 2. For Hubble, that would be like your FLT.FITS files, your FLC.FITS files. And then we're going to take those and we're going to create deeper stacks, mosaics of them, for all of the imaging data except for the galactic bulge time domain survey. Then we'll take those deeper images and we're going to create catalogs and higher level science products for you, including source catalogs, photometry of variable sources. We'll have libraries of empirical PSFs and a lot of other things. At IPAC, which is a science support center, they are going to be taking all of our calibrated imaging from the galactic plane, galactic bulge time domain survey. They're going to stack them and create catalogs of this one particular survey for the community, including generating light curve catalogs and variability catalogs. Then IPAC is also responsible for the higher level processing of all the spectroscopic data. And so they will be producing products like 1D spectra and catalogs containing spectroscopic measurements. IPAC is also responsible for the call for proposals and grants management. And so if you submitted a Roman proposal, then you have used IPAC's website and proposal submission service. In addition to who does what, that's a little complicated, we also have data that's coming in 2 different flavors. We're going to have prompt products that are available right away, and we're also going to have data releases for Roman. For the prompt products, these are going to be calibrated single filter images as well as single filter catalogs. These are ready almost immediately after receipt of the data. All data on Roman are open access immediately. There's no proprietary time. And so, within a day or so, you're going to be getting images and spectra from anything that's taken on the telescope. And IPAC will be generating immediate microlensing catalogs. These are great for exploratory work and preliminary analysis. They're great for helping you to develop your analysis workflows. But I will warn you that these are not uniformly calibrated. Any data that's taken from the telescope will run through whatever calibration is available in the moment. We will also be doing data releases, and we're periodically here at STScI will be uniformly calibrating and processing all the data again, doing force photometry to create multi-epoch catalogs, creating deep mosaics, and multi-dan photometric catalogs. These are the ones that we're producing at STScI. IPAC, as well as the community-funded science teams called the PITS, will also be doing data releases. I don't have any details on what they're producing, but this gives you a sense of what you'll be getting from STScI. And so we're also developing a special platform to allow you, the users, to get access to the data in the simplest way possible. And we're calling this platform the Roman Research Nexus. And this is really where scientific discovery is going to happen. The Roman Research Nexus is a cloud-based platform. It will enable you to get access to the data and do scalable analysis. You'll log in through a portal and get a pre-configured Roman environment with custom software, and you'll also be able to install your own software, whatever you need. We're also enable team collaboration, so you can share files with your team. You can even simultaneously edit Python notebooks, for better or for worse. There's no installation needed. If you have a MyST account, you have access to the Nexus right now. It's open to everyone, and I would encourage you to go in and try roman.science.stsci.edu and check it out. Feedback is very welcome. This is what it looks like when you log in. It's a Jupyter Lab environment, and inside it, to help climb the learning curve, we have a bunch of bite-sized tutorials. For example, how do you interact with the Roman ASDIF file format? We are no longer in the land of FITS, people. We are doing ASDIF. So there's a learning curve, but once you get in, I think you'll really like it. We have instructions on how to work in a cloud environment, how to visualize data. And these little bite-sized tutorials are strung together in pedagogical workflows. And so it'll give you a sense for how you actually do a larger type of analysis on Roman data, including visualization, simulations, or even observation planning. And then I want to say, I want to recommend that you follow us on social media. We have a special site for scientists. This is not meant for the general public. It's Nancy Roman Sci, and we post all kinds of updates, a couple times a week on what's going on in the mission, new tools that are coming out, and so it's worth giving this a try. It's on all of the main social media platforms. And finally, I just want to end with a shout out to Nancy Grace Roman. She was NASA's first chief of astronomy, a pioneer for women and for science, and it is Nancy Grace Roman for which our telescope is named. Thank you.
Coming soon. Christy.
How long after launch will data start flowing to us?
Excellent question. We have a 90-day or 3-month commissioning period. And so there will be no data flowing then. But assuming that we stick to the 90 days, then on day 91, 92, you'll get data. It takes us a few hours to process the data. So, but within 48 hours or even 24 hours, if you go on the Nexus or to MAST, you'll be able to access the data.
Okay, any other questions? Aida?
Are you already talking to the Ruby and LSST? Are there already projects in common?
I think there are projects in common, and most of them have been driven by the science community. I have been in conversations with their scheduling team there. We have a fixed 5-year mission plan based on these predefined surveys and new programs in the community. They have a more of a dynamical scheduling system, so we have been in conversations of can we try to do simultaneous observations of the same fields? Would that be interesting? I think it really would be. So we're doing things like that behind the scenes on a project level basis, but the combined analysis, there's 88 different ideas and efforts in the community to try and do lots of things with Roman and Rubin. Yes.
Okay, there will be more time for discussion when we get to the panel. Let's thank Christy again. I had to say, we are so lucky to be living in this era. So next up, we have Chris Evans, who will talk about the ELT.
Thanks, Janice. So good afternoon, everyone. So you'll notice, my day job here at the Institute is as the HST and JWST project scientist for ESA, the European Space Agency. But I'm going to be talking to you today about the next stepping stone in our future facilities, which is the Extremely Large Telescope, ELT, which is being built by ESO at the moment in northern Chile. Thanks to the organizers for the chance to talk about ELT. So I worked on ELT for many years in my previous role before moving to ESA, and I'm still connected to one of the instruments. So it's a great pleasure to be able to give you some of the highlights here with some slides borrowed from a talk by Jarle Brinkmann, the Director for Science, who gave a great talk and an overview of ESO at our recent Hubble and Webb conference in Vienna. So just to set the stage, so ELT, the Extremely Large Telescope, is now being built by ESO in northern Chile on Tierra del Amazonas. And I think it's a really exciting stage for the project because, I went to my first ELT meeting in 2004, and for a long time we've been working on the design and development, which is always the computer-aided design, images, graphics, all the work on the instruments as well as the observatory. But now we have a growing construction project in the desert in northern Chile. This was the latest image that Jarle showed just last month in Vienna. And his updated timeline was the construction is now more than 70% complete. They're anticipating first light in late 2029 with first light of the science instruments in late 2030. And you can see here on this image that the dome itself is now closed on the site. So this means they're now doing more work on the superstructure inside the dome and that the main part of the dome construction is complete. So we've moved from this stage of like that long haul towards the design and development into a real construction project with something the size of a stadium taking shape in the desert there, which is tremendously exciting. So just to set the stage for the optical design of the telescope itself, this just takes you through the optical path for the main part of the telescope. So it's a novel 5-mirror design. There's this colossal M1, which is nearly of order 39 meters across, comprised of nearly 800 hexagonal mirror segments, most of which are now manufactured and ready to go. And then it relays the light to a 4-meter M2 mirror, tens of meters above that primary. So if you imagine taking the Blanco or the WHT and suspending that tens of meters above the ground, pointing downwards, that gives you a sense of scale. And then it relays that to a 3rd mirror, a 4th adaptive mirror. So there's ground layer AO in the telescope itself, and I'll say more of that in a minute. And then there's a flat M5 mirror that redirects the light to the instrument platforms. And in addition to the M1 segments, there's the manufacturing and development of all the other optical elements is making good progress with the different procurement and manufacturers in Europe and ready to be shipped as well. So the instrument platforms, there's Naismith platforms on either side of the main primary. Each of these is large enough to have one of the unit telescopes, the VLT. So if you can just picture that, an 8-meter telescope and its infrastructure there on this colossal Naismith platform, which we need here for the focal station for the instruments relayed to the different instruments that will make up the instrument suite for the observatory. And I'll just walk you through those very quickly to give you an idea of the capabilities that you can anticipate as the instruments come online over the first years. Again, just from Jarle's slides from last month. So what will most likely be the 2 first instruments will be Mikado and Metis. So Mikado is a near-infrared AO-corrected imager and spectrograph over the sort of I through to K band. And Metis will be a mid-infrared imager and spectrograph with an IFU capability with a high-resolution mode as well. And there will also be an AO module early on to do multi-conjugate AO over a 1 or 2 arc-minute field that will feed the infrared camera Mikado. And then there will also be as part of the first instrument suite, there will be a near-infrared IFU called Harmony. And you can see on the right here, the different logos from the different institutions and organizations involved. This is a real cross-Europe effort with many partner institutes working together in partnership with ESO, and also including partners in Canada and University of Michigan as well. So there's international collaboration with the European partners as well. Thereafter, there's 2 further instruments that are now signed and going into the earlier stages of design and development. So that's Andes and Mosaic. So Andes will be a high-resolution spectrograph from as bluewoods as they can go through to the K-band, potentially, with R of 100,000. And Mosaic is a multi-object spectrograph with both visible and near-infrared multi-object capabilities and infrared IFUs as well. And I'll say a bit more about that in a moment. Again, you can see here the consortia are particularly large with tens of partners working together to bring those resources together, hundreds of FTEs to design and construct and deliver these instruments. Just a quick word about AO and kind of setting your mind thinking about the scientific synergies, particularly with Hubble and Webb, but also building from Roman and looking forward to HWO as well. So there's different adaptive optics modes on the telescope with lots of different abbreviations, but you can think of it as there'll be some AO-corrected observations in the near-infrared near the diffraction limit over a very small field where you're really putting all your correction into a small patch of the sky or small object field. There's an intermediate mode where you do this multi-conjugate AO with a secondary DM to correct a 1 or 2 arc-minute field with good correction, again, mostly in the near-infrared. The performance as you go to the shorter wavelengths drops off pretty quickly just because of the image quality you need. And then there's a broader AO correction, ground layer AO, over the full ELT field of view of multiple arc minutes. But you can think of that more as enhanced seeing. So it gives you the stability you need to do the observations, but you're certainly not talking about the diffraction limit across the whole field, and particularly not at the shorter wavelengths. Just to give you a visualization of that, so these are ground layer AO simulations in the H-band. So there's the atmosphere. You have to take into account the vibrations from the telescope structure, and when you use the GLAO, you get more of that energy in terms of n-circled energy or n-squared energy into your spectrograph. But it's still sort of this enhanced seeing option, but with the benefit of a 40-meter collecting area and a 10 arc-minute field of view. So a few quick words about Mosaic, the multi-object spectrograph, because I think that links very naturally to the science cases we're talking about this week. It's also a project I worked on for a long time before moving to ESA, and I've since become reacquainted with it as the chair now of the Survey and Publication Board. So there'll be two main modes of the instrument, a multi-object spectrograph mode with fiber bundles picking off individual targets, so with a multiplex of over 100 in both the visible and near-infrared, and also a multi-IFU near-infrared mode with a few IFUs deployable across that the field. Again, just to kind of match that to the image quality, so the only way you can do this with the fiber bundles is to have multiple fibers together, but you're not resolving the objects within those fiber bundles. That's just to couple the light into the spectrograph. So again, you're thinking about this enhanced seeing of 0.7, 0.8 arc seconds coupled into the observations or into the spectrographs and feeding different modes with R of 5,000 and potentially a high resolution mode as well. And so just to kind of, my naive way of thinking about this is if you can observe fields with Hubble or with JWST, and now thinking ahead to Roman and Euclid as well, the sort of image quality or angular resolution you get from those current observatories where we're doing the imaging, we don't have the collecting area to do the follow-up spectroscopy, but ELT will give us that. So just as an example, this is more in sort of the turf Paul was talking about this morning of sort of LMC-ish, but there are other lower metallicity systems at 1-2 megaparsecs. We have this exquisite imaging from Hubble across galaxies like NGC 55, and matched to that angular resolution, we will have the capability to do the spectroscopic follow-up. People have been trying to do this with X-Shooter and other ground-based instruments. It's incredibly tough work doing this for individual O stars or young massive clusters. But if you have a 40-meter primary coupled with a high-throughput spectrograph, you can imagine building up samples of hundreds of objects very quickly across galaxies like this. Similarly, if you go to the evolved stars, so this is a part of the WLM galaxy observed with JWST. And this is a color magnitude diagram from Christie's paper just a couple of years ago. So again, here you've got this beautiful imaging with JWST. We can go and do the spectroscopic follow-up of these sources with the ELT. And if you look at the CMD here, it goes from sort of 20th up here at the top of the red giant branch down to 29th magnitude. We're not doing follow-up spectroscopy down here, but you can pick off these targets. So if you want abundances, dynamics on the evolved populations in galaxies like this at the edge of the local group and going out to larger distances, then you can start picking these off. Just to go back a little bit, we did some early simulations for a precursor of Mosaic, looking at what sort of performance you could expect in the calcium triplet with a 40-meter primary, with the latest AO simulations at the time. And I think to order of magnitude, these are still valid. You can imagine picking off the top of the red giant branch in a galaxy like WLM to build up samples of hundreds of stars, coupling that to the image, and doing that for multiple galaxies out to several megaparsecs. And then you're really probing the low metallicity tail in these metal pore systems. And with that, I will just direct you to, on the ESO web pages, there are multiple different webcams where you can go and see the progress of the construction and views from Paranal, and stay tuned for the first observing call, I think, because that will be coming in a few years, and it's not too crazy to think about what observations we have from Hubble and Webb already, what we're going to get from Roman, and what we're getting from Euclid, and where we need that follow-up from the ground. So thank you.
Any questions for Chris? Aaron's just blown away. Well, there will be more time because we're going to welcome all three speakers back up when we do our panel. So let's give Chris another round of applause.
Surely I get more than 5 minutes. Yes. Can everybody hear me? It's delightful to speak in this room, and the room is full. Thank you all for coming. Got it?
10 minutes, right?
I thought I was told 24.
Well, last but certainly not least, Jason Tumlinson will be telling us about NASA's next flagship mission after Hubble.
After Roman.
After Roman. You know where my head is.
Just save time, just all the slides.
All my good jokes are getting like exposed here.
It's a conspiracy. I'm
wonderful.
Avert your eyes. There we go. How about play?
Okay.
Ah, there we go. Okay. Right, to the Habitable Worlds Observatory. This is going to go really fast. Every 10 years, astronomers get together. They decide what are the big projects we want our community to do in the next 10 years. They send those recommendations off to the funding agencies. Habitable Worlds Observatory was the Astro 2020 top recommendation for space facilities, following on all the other things which we have built and used or will soon launch. So this is America's, NASA's next big thing in space observatories. What is it? Well, we like to think of it as not only a big telescope that's going to do a lot of amazing science that I'll tell you some about, but it really is a super Hubble. In other words, it operates in the UV, the optical, and the infrared. And it's designed with many of the same capabilities that Hubble has for spectroscopy and imaging, but times 1,000, or in some cases times 1,000,000. And this is just one possible rendering of NASA's different architectures, showing the instruments in the back. To give you a sense of scale, you could put an entire Chris Evans in one of those instrument bays. That's how big it is. These are two of the concepts that are currently being carried. This is my favorite because it's bigger than 8 meters. Maybe up to 5 instrument bays. Actually, you can draw a 10-meter circle around the corners of those mirrors, so you could arguably call it a 10-meter telescope. Up to 5 instrument bays, including UV spectrographs, high-resolution imagers I'll mention in a minute. Here's another visualization of the packing inside the telescope. This has to go on a big rocket, so it's got to go on the SLS if that still exists, but more likely Blue Origin, New Glenn rocket, or the SpaceX Starship. It's a big, big telescope, and it barely fits in even when you fold it. It's an amazing telescope and instruments. This thing has to be stable enough to detect and study 30th magnitude Earth-like planets, less than an arcsecond from their parent star. That's the most challenging observation it's going to do. So the ultimate stability has to be built into the telescope. It has to be actively controlled more frequently than every second to maintain that level of image quality. I'm actually not going to talk about much about the exoplanet case for the obvious reason that this is a Galaxies conference, but it will have a high performance coronagraph where you ought to be able to pick out the little blue dot that's Earth and do spectroscopy to distinguish Earth and Venus, because one of those is a place you might want to live and the other one definitely isn't. Think about the high resolution imager as what we have on Hubble with C3 or NIRCam, with diffraction limited imaging at those wavelengths, but for a 10-meter telescope. And then the superpower is the UV spectroscopy. This is just a very crude sensitivity map comparing Habworld's limits down at the nanojansky level in different telescopes and different times. But look how far down this goes, right? That's 10 hours and it's already 32nd magnitude. 33rd magnitude is in the conversation for this thing. And I don't think anybody's ever seen one of those. We don't know what the sky looks like at 33rd magnitude. So what can we do with this unlimited power? Well, Habworlds enables a very wide range of transformative astrophysics. This is what I call the Habworlds bento box. It's just a whole bunch of stuff that was submitted in terms of by the community, science ideas, 1.4 million individual UV shutters, which you can configure however you like. So this is essentially the MOS device on NIRSpec, but translated to the ultraviolet, the micro shutters. We might do it with little mirrors. We'll see. Deep fields mapped about 8 times faster than Hubble and 4 times faster because of the aperture and the image quality. 29th magnitude point sources in well under an hour. All this kind of amazing stuff. Resolving the outer solar system almost as well as you can do with little telescopes that are out there in the outer solar system. So I want to inspire you to think about science you can do with this, right? This is something that, as I look around, most people in the room are young enough to be able to use. I expect to be, so most of y'all will be as well. This is Julianne Del Canton's beautiful fat image of Andromeda. We've all seen this many times. You can't even make out all the detail because this is on the screen and it's pretty lousy resolution. But if you tile this field with the high-resolution imager of Habworlds, that's what it might look like. It's a 2x2 detector footprint. And you can do that in a small fraction of the total time that it took. So this is stellar populations work at very precise photometry, everything you're used to doing with the high-resolution Hubble images. There's some simulations of what the outer disk and the bulge might look like, but in a fraction of the time. Even more compelling, I think, is that the gas here is also interesting. That, not coincidentally, is what I work on. So the gas processes that shape galaxies, you can do intensive multi-object spectroscopy. Now, I think I just saw Svea. Yeah, there you are. Yeah. Remember we tried to do this with M83, and it's really hard to do it with COS because it takes like 5 to 10 orbits per target, and you get like, I think there's 18 places people have put a COS aperture down on M31. Well, if you use this micro shutter array and you just pave the sky of M31 with these shutters, there's 1.4 million shutters in every footprint you take. You can probably use 100 or a few hundred of them at a time if you're willing to put up with some overlap. And when you tile this, you're potentially talking, I mean, there's actually, in the figure I drew, there's 584 million individual shutters. Take your pick, right? And now you can do these highly multiplexed UV spectroscopy programs where you might collect, tens of thousands of individual spectra on a single galaxy. To me, that's pretty unbeatable. You may have seen this cartoon. I don't know. I like it. We tried really hard to make it work. But it's one of my great goals to retire the cartoon. Vita, our Foggy postdoc here at JHU, made this wonderful figure for me using some form of AI. I want to turn this cartoon into data. I want to turn the cartoon that we drew, because we don't really have pictures of the actual circumgalactic medium. I want to retire the cartoon and do it in data. We're going to do this with habitable worlds, right? Super sensitivity in the ultraviolet with the micro shutter array. You can put that down wherever you want. This is an example of the face-on M83 where you're doing down-the-barrel spectroscopy for hundreds of sources. This is emission, right? This is the classical, poster child for starburst galaxies. Put a bunch of these MSAs down there, and now you can look at sub-parsec scales. Actually, the shutters are about 10 parsecs in size on the sky at about 10 megaparsecs. So now you're really dissecting these flows from and into galaxies at very high resolution and very faint limits. And then another thing I'd like to do is turn this thing on the Redshift 1 universe and get emission in 02, 03, 04, 05, and 06 all at the same time, counting up all the metals in the circumgalactic medium at high redshift. So it's a super, super powerful thing to be able to do. This is a great science case that Bethan and Danielle contributed to the HabWorld Study Committee. This is the proof that you need an IFU capability that's different from the wider field MOS. So with the wider field MOS, you do have to have some kind of tiling or progressive scanning of apertures on the sky. With the IFU, you're going to get everything in that field, probably about 10 arcseconds square in one chunk. About 0.2 arcsecond spaxels, that's the goal at least. Imagine what you can do with this. If you're not starting to nod your head and wave your arms that you want this to exist, maybe I shouldn't have come today. You've probably also heard about the idea of resolving the very massive stars in very dense environments. This is another place where HabWorlds will excel because its ability to take high-resolution UV images. And we're working on exactly how high resolution that needs to be, but certainly as 1Zwicky 18 or other nearby galaxies, little dwarfs in the neighborhood, you want to be able to resolve those things. Just to pick up one little bit of high redshift, if I draw a contrast between depth and resolution between Hubble and HabWorlds, and I did it with Hubble so that you can think about the effect of doing this in the rest frame ultraviolet or at the low redshift universe in the observed frame ultraviolet where these star frame regions pop out. These are the little blobs that are going to come out at 30-second magnitude when you're doing deep observations. And now, suddenly your galaxies don't look like the faint smudges anymore that we're used to from the original deep fields. So HabWorlds is currently being shepherded by a project office that's based at the Goddard Space Flight Center and NASA's JPL in California, and there's a committee of astronomers from around the country, including a few of us here. There's Janice, there's me, who are developing science cases and helping to guide the technology development for the observatory. We're in a very, very early phase. We're at the stage where we're trying to figure out how big does it need to be, which instruments should it have, and we're working on science cases we call the driving cases, those that really drive the telescope and the performance of the instrument. And they're looking at writing down the first stage of what's so-called level 1, the really big requirements, later this summer. There are also active participation from abroad. This has become a really robust and I think high-performing team. These are the people you want to work with if you have ideas. There is going to be a call out very soon for instrument studies. That can be almost anything. So anything you want to put on this observatory of any kind, imaging, spectroscopy. We have, I think these things are going to run the full gamut. And this is not too onerous. It's something that, an individual science PI should be able to pull off. And it's very, very important that we collect the community's ideas at this stage and not leave anything lying on the table that we'd like to pick up. So look out for that. This is a place where you can go to contribute and learn more. In particular, hear about, there's what's called a Science Interest Group, or SIG, which has been organized to support the CSIT in its efforts. And that's a wide open community group. Anybody can contribute. Scott Gowdy at The Ohio State University is the CSIT's liaison to that group. And you can find information there about how to join that. That's where you would go to contribute science ideas and learn more about the project. And I think that's probably, yeah, sorry, this is the community-based science interest group, those QR codes. And this will be, of course, in my slides online. Anybody want to snap that while I'm standing here? Now's the time. And Janice is going to yank me pretty soon, so we're done.
Can you put the last slide up again?
Yeah. Okay, I'm going to leave it there. But I think if I advance it, it drops again for some reason. But I think almost everything you need to know is in one of those sources.
Questions?
Hi, Elena.
Okay, so we've learned a lot about how to operate and calibrate NearSpec, and it's hard.
Mm-hmm.
It's hard. So what is the time frame for us to get the kind of feedback to you and people that are developing instrument cases to know, so that you can make informed decisions that allow you to calibrate it better than we can calibrate NearSpec?
Yeah.
Because we want better than 5% flat fields.
Yeah.
That you're getting right now.
Yeah, that's a very good point. So the call for instrument proposals is not out yet, but I understand there will be instructions to PIs specifically about calibration. Now, there was a workshop about the instrument proposals at the beginning of last week in DC that I went to, and a few other people probably were there. And people were asking that question, and the answer was, we really haven't thought about calibration very much. We should do that. And I said, yeah, so we'll be sending them some of our local expertise to talk about that. And another thing is that through the SIG, which is the open community group, if there's very particular things like, my project will fail if I don't have a 1% photometric calibration, then you really need to be contributing that so that it gets noticed, because we won't really think of that ourselves. But you make a very good point.
Okay, so what we're going to do now is take a little bit of break of people looking at you while we welcome the three speakers back up to the front. Take a look at the screen and take a few minutes to turn to your neighbor or group of neighbors and talk about the question. If you could make one key measurement with future facilities that would fundamentally change our understanding
I didn't want to go blind.
of the low-metallicity universe, what would it be? So the idea is that you'll have a few minutes to talk, give us time to set up, but then there's a QR code at the top, and there should be a Slido there if it's all is working well.
No, which one's the magic card?
Then we're going to do a little bit of a game and ask the people up here what they would point the telescope at. What would be their first observation that they would want to take with the facilities that they've been working to develop. And then we will reveal what the audience has to say. Okay. So let's give it 2 or 3 minutes. Please go ahead and introduce yourself to your neighbor and talk about what would you do to solve all of our problems. All of
I'm Mark. So what would you do? I would put
Have time, like another 30 seconds for you to put your answer into Slido. Okay, I'll leave this up. Actually, if you haven't taken a picture of the QR code, can you do that now? Because I'm going to switch the slide. And I think we have like 10 answers so far. So, 20. Oh, we have 20. Oh, wow. Okay. Let's go to the version of the question for the panelists. So this is a little bit of a different flavor, but it's a little bit of an icebreaker too. Thank you to Chris for suggesting it. So given all the work that you're doing on your facilities now, what's the first observation you would make if you had the chance? You can't say what's for Dirty Door. I'm just kidding. I know what Chris would say. So let's go from Chris to Christy to JT.
So Thanks, Janice. So yeah, I think the obligatory, you commission it using 30 door. You can point the eye a few observations at the center there to follow on from what Paul was doing. But more seriously, I think just having the large area, the large field of view with the multiplex, we can really start to go and build up samples in the sculpted group galaxies, in the galaxies at 1 megaparsec for the first time. And I know Maud and others in the audience have been trying to do this star at a time or with a handful of stars, really working that signal to noise. So I think going to LEO A, Sextans A, NGC 3109, picking a field there, getting an amazing sample of O stars at excellent signal to noise at R of 5000, just that first pointing would be just, several PhDs worth of data and would be really exciting.
That would be very transformative.
So if I tried to negotiate this when I got the job, but they didn't give it to me. I would just map out all of the nearby galaxies to great depths, not just their disks, but their whole ecosystems, their halos, their satellite systems, and just create an incredible treasure trove of nearby galaxies in the local group and a local volume, and like we've never had that before.
Yeah, that would be amazing. A lot of the work that we've done with HST, as you know, we're only covering the inside of the
very
disks,
small part.
Yeah, the central star
really
forming
interesting
disks,
science
galaxies,
that's happening. Yeah,
and all those outskirts out there. Yeah,
yeah,
and left out. JT.
Yeah, so basically my whole life I've been taking one UV spectrum at a time. Realize this, and so being able to do 100 or something is really powerful. The science question that really fascinates me right now is the question of recycling through the circumgalactic medium. So it almost has to happen for all the other mass budgets of galaxies to work out, but we don't really see it, and we don't know the timescale for it. So imagine, and it's probably true, that all the normal matter, the oxygen, the nitrogen here in the room actually did leave the Milky Way at some point, because that's how stellar outflows work, but it had to come back. And so measuring the timescale of that using the kinematics of these super winds and the UV MOS mode is sort of my favorite project. Actually measuring the flows and then finding out where they turn around and come back would be my cycle 1 program, I guess.
Yeah. And so, given that we have the three of you here, people think a lot about how the facilities might work together. But for this particular science area too, how we can think of a road, I mean, UVEX is not represented here, but we should think about UVEX too. A roadmap for solving our problems going with the combination of facilities combined. So any thoughts on that?
Well, I'll just start with Roman's going to be the finding machine. So we'll set up the other observatories set them up for success for follow-ups.
Just to follow on from that, so I think, doing the larger areas that we can do, going larger areas than we can with Hubble at the moment with Roman, pick out those larger samples that we can then do the spectroscopic follow-up, and then that's the stepping stone to observations at even lower metallicity with hub worlds in the future. So.
Yeah. In my area, circumgalactic medium, IGM, quasar absorption lines, the ground-based telescopes and space-based telescopes have always been very complementary. Only in space can you cover the UV. From the ground, you get your wide area survey, so you can pick your targets, and then you also get your optical spectroscopy. And I would expect that analogy, that holding hands and kumbaya together, would continue as you go deeper and wider. So finding just the right target to look at, and then doing the ELT spectroscopy, and then combining the HabWorld's UV would be very powerful.
HabWorld's UV, yes. Okay, I have no idea what this is going to look like, but we're now going to display the current results to the Slido poll. Should be here. Yeah. Yes.
I can tell you that high sensitivity by a few is on the top, like 7 votes.
7 votes.
Very many more people need to vote.
Yeah, I can vote for 8 for vote.
You can continue to vote and it will change in real time. Yes.
I'll go stuff the ballot box.
So a comment about the high sensitivity UV IFU. We were talking earlier about having people write white papers for Hubble. And I just want to tell a little bit of a story about how community input can actually really make a difference to missions. So as some of you know, we hadn't been considering a UVIFU for HWO maybe even just a year and a half ago. But with the input from the science cases, especially from this community, people who want to study low metallicity stars and gas, as you've heard throughout today, there was a really strong case for UVIFU, and now we are recommending that people put in concept studies for that instrument. So, you know, if there are things that you are thinking about, questions you want answered, it is really important that, you know, tells a story of how important or how impactful the collective voice can be. So I wonder if people have, I guess, is there anything surprising in this uncertainties in this panel? I think
whoever wrote spectroscopy greater than 50,000, I owe you a drink.
So now a lot of people are going to be putting that in, so he'll buy drinks for everyone, right?
I'll also piggyback on what Janice was saying about community input, because the 4 surveys I was describing in my talk were defined through a community process. And 3 of the 4 surveys were roughly sketched out to focus on the science drivers of Roman, which are dark energy, the expansion of the universe, and exoplanets. But you can design a survey to study dark energy and leave a lot of other science on the table, where you can optimize that survey with input from many in order not just to measure dark energy, but to also be able to provide, you know, the wide field imaging and the right filters with the right cadence and the right field of view in the right part of the sky that enables all sorts of other kinds of astrophysics surveys. And so through a community process, we received science pitches and white papers with input from over 1,000 scientists from over 350 institutions around the world. And it changed the way the surveys were defined. And it's through a process like that that we also got the galactic plane survey defined and implemented. So it's a great, I think, strength of our community that we do this. And I think it's a credit to NASA and the institutes that support NASA, like STScI, that support such a community-driven process, because it doesn't have to be that way. And it's not something I think any of us should take for granted. And it is really impactful and powerful. And I think we get the most out of these telescopes because of that.
Okay, so I did say that we could come back and open the floor up for questions and comments again. And so before we move on to our final audience activity, we'll do just that. Yep.
I had a question that's not necessarily scientific, but more regarding like the sheer data volume that like Roman will have, and imagine some of these other might also accumulate. What is kind of like, how are we handling this as a community?
That's an excellent question. From the Roman perspective, we've solved the data storage and handling and analysis to make it broadly accessible to people from not just the US, from around the world, by having everything on the cloud. And so all of the data for Roman will be on AWS and managed that way. Different surveys are doing it differently. LSST has all of their data on the ground, on premise, we should say, at Slack. Not on the cloud. The cloud is actually on the ground, but you know, it's easy to think about it like up there, bubble, with access for the community on the Google Cloud, but the data is actually not on the Google Cloud, it's at Slack. And so they've solved it a little bit differently. The interoperability, though, between those data sets has yet to be accomplished or designed or implemented to do on a large scale. So I think there's some major challenges ahead on how to navigate that. And there are many of us, including myself, that are thinking about how to do that, but it's complex because you have facilities, observatories, and data that are funded through different federal agencies, whether it's NASA, DOE, NSF, and they all have their own priorities. My priority is to make sure that the work we're doing here is successful for Roman. And while I really want to be able to marry Roman and LSST data, my first priority is for Roman. And that's a pretty common thread across, different data. And then similarly, Euclid, right? Euclid is something that we also want to bring together. And there's a little bit more in the works for LSST and Euclid, sort of as a more formal plan on how to get that data set together. But it's still kind of a future thing. It isn't in place now. I will say that the US is hosting the Euclid data at the URSA archive at IPAC, and that data will be hosted on AWS on the cloud in the same region as the Roman data. And so our plan is to be able to go into the Roman Research Nexus that I mentioned, and you can actually pull the Euclid data from the URSA archive into the Nexus and do analysis with it in situ with your Roman data. So there are pieces that are being put into place. Everybody's everybody's kind of designing something they think is going to work best for them, and they're all different flavors of it. Having one like happy unified data lake or data ocean is something that I would love to see happen, but there's a funding shortage, really, not for a lack of desire, but more for a lack of time, infrastructure, and funding, I think is the biggest challenges. I don't know if either of you want to add anything to that.
Thank you. So I see, I have actually a question for all of us, and then that will serve as a segue to the final question on Slido for today. So WensWiki 18 is the poster child for the conference for many things. And a question is, if we want to be able to study the gas and stars, individual stars in WensWiki 18 in detail, it's hard because of what nature has provided to us, right? It's at 18 megaparsecs. So we have been searching for decades for other galaxies that would be just as metal poor or more metal poor than WensWiki 18. What is the possibility that we could actually find something that was closer with as many, expected high mass stars? It goes back to, some of the questions we were talking about earlier today about what is the expected density of these objects, both locally and throughout cosmic time. Anyone want to start the conversation?
I mean, the idea would be that we haven't found them because they're faint, right? I mean, what else wouldn't we have that? So meaning they're going to be lower mass than WensWiki 18.
So a lot of the BCDs, blue compact dwarfs, even extreme emission line galaxies were found not in magnitude limited surveys early on, but they were found in emission line surveys. And that gives you a different selection function from, that would fight against trying to go down and finding all these objects and having to sift through all the objects to find the faint ones that are actually close by. So, I mean, we have been searching for many, many decades, and now we will have Roman. Christy, you also mentioned that perhaps we can also mine for very metal poor galaxies with new Roman data. Rachel, did you have something to add?
Yeah, so the thing is I forget, what's the mass of WensWiki 18?
10 to the 8th, 10 to the 9th.
So solar mass or total mass, halo mass?
Total mass.
Okay, so much below that, you don't hold on to gas into the present day, right? So we have old metal poor systems in our halo, right? The ultra faint dwarf galaxies, but they couldn't keep their gas. It's environment limited, but they couldn't keep their gas. And I'd be very surprised to find things much lower mass than that. You'd have to have some. Right. Well, we found one, right? We found the relic earlier in the year that has H1 in it, but it's never formed stars, right? Like those are the kinds of objects that would be smaller than that. So I don't know where the cutoff is exactly because it's very fuzzy.
Well, then we go back to, the question that everybody always asks, why does WensWiki 18 exist, right? And we've talked about that for decades as well. How can something so metal poor, I mean, there's DDO 68, okay, but maybe it doesn't have stars as massive. But we have not been able to break the WensWiki 18 record in the volume close by. Aida.
So I think you need to ask the cosmologists that do nearby large-scale structure, because you tend to find this in low
Voids.
galaxy density environments. If we know where those are, that's where we should look for more. But because there are low density galaxy environments, there's few, by definition, few galaxies nearby.
So we've gained a lot of amazing data through big spectroscopic surveys like the STSS,
right.
Things like ESI, and we are finding really metal-poor galaxies through those avenues. But usually their selection function, as you said, is some magnitude limit. So you're typically reserved to the brighter objects. However, in these surveys, they do have other selection functions. They go after things that they think are quasars, so really compact blue objects. Well, blue compact dwarfs can be confused for them, so we can pick up sources through good fortune in that way. Alternatively, instead of going for objects from imaging, you can go through slitless spectroscopy.
Right.
The challenge there is that you lose a lot of sensitivity. So I would say...
But it would get the highest equivalent with objects, for sure.
Yeah, well, if you're interested in the strongest line emitters, then the continuum will be faint, but the line will be strong. But you're still fighting against that increased background. So one alternative is just to go after the faintest systems. And for example, what I've been doing in my work is looking at photometrically signals of lots of H alpha, but weak auction free. That's something that Peter has also done. Then you can push to the faintest systems and target them with spectroscopy. That's another avenue.
And then the trick is to try to find them closer by. Matilde had her hand up.
Yeah, no, you mentioned it before. You mentioned UVEX as well. There will be also UVEX in the next few years, and UVEX will do a non-SCI survey, and so probably we will discover a new parameter space with very low mass and metal poor objects, and that could be a good starting point to see if there are non-SWIC18, because that's one of the good things of UVEX is the sensitivity in the imaging as well, only the spectroscopy.
Danielle, do you have something to add?
I have an unpopular opinion that 1Zwiki18 is weird and should not be our poster child for extremely metal poor galaxies. And like Leo P, which is much closer and very low mass, actually sits on the MZR and LZR. It's the only galaxy that we know that does that. And with these really deep surveys that we have coming up, we can actually detect things like Leo P out to close to 100 megaparsecs. And so we're going to find a ton of these tiny building blocks coming up. I mean, doing it with spectroscopy would be great as well with this slitless spectroscopy, but we got to go deeper to see these smallest building blocks that are going to be truly chemically pristine things, not things that have had weird past interactions and have weird old stellar populations and stuff like that that are really fun but hard to understand as well.
I think the challenging contradiction with the Leo P case is that, okay, well, you want something to form high mass stars so we can understand high mass star formation at very low metallicity. And that's sort of, in a different part of parameter space than these small building blocks.
Yeah, but you could build up a sample of high mass stars by building up a sample of Leo Ps too.
Oh, and then we get into arguments about the IMF. Yes.
Yeah. That argument would exist regardless of what system you look at.
I'm glad that Danielle brought that up because we're ignoring the gas.
Yes.
It's mostly a star conference, but we're ignoring the gas. And all of these metal poor systems, if they're similar to the dwarfs that we see around, like your IC1613s, your Leo Ps, your 1Zwiki18s, they're all going to have huge atomic gas reservoirs. They're all atomic gas dominated. So maybe an avenue to look for these things is how Leo P was discovered, was through the alfalfa survey, was through an H1 survey. So maybe we need more H1 surveys, and I think something like the synoptic array, the DSA, will maybe be doing a little bit of this.
Good point.
And I also would like to piggyback on what Danielle said. Like, don't get me wrong, I'd be the first to also point an IFU at SWIC18, but also just the stellar content of all the low metallicity dwarfs that we have around us. WLM, NGC 6822, IC1613, which are the more metal-rich ones, but still sub-SMC. But then also Sextans A, Leo A, Sagittarius dwarf irregular. We do not have a complete sense of the massive stars in those galaxies, and I think with these types of instruments, we'll finally be able to understand these low metallicity environments locally.
Absolutely, low-hanging fruit for HW.
Can I, and just to follow on from that as well, I think that's where thinking of the Hubble white papers as well, the idea of really pushing that as far as we can with each of those stars with deeper observations. And then we get ELT, where we can then go back and do the multiplicity monitoring in those systems. And then that leads into UV spectroscopy with HABWELS as well. And for me, listening to Emma's talk today and others, it's what are the progenitors of those things that, we're seeing galaxies at 300 mega years, we're seeing the nitrogen enrichment. Paul showed in his plots that we're not seeing those stars at the very hot end. So what are the stellar evolutionary tracks looking like at those metallicities? And we just need to calibrate that with as much empirical information as we can locally, using Hubble, using ELT, building on Roman, leading towards HABWELS, and try and understand those channels and what progenitors they become with the supernovae to give the yields we see. So I think there's bringing all those two together and thinking about what Hubble will be doing in the next few years as well will be critical.
Good way.
Well, did you have anything to add?
No, this is a great way to tie it off.
So, thank you all for a fabulous discussion. I hope that seeds, future discussions throughout the week. Let's thank our panelists again and and all the speakers today for a wonderful one.
So, before we wrap up,
announcements.
Yeah, we have the reception happening at the cafeteria like right now. For those staying in hotels and wanting to use the shuttles, they are gonna, starting from now, every 30 minutes until 7, they will be in and out from Space Telescope to the different hotels. And yeah, that's it, right? You all.